The defining promise of a hash table is average O1 time complexity. In theory, inserting, deleting, or looking up a piece of data takes exactly the same amount of time whether the collection holds 10 items or 10 million. Every O1 operation requires a physical footprint on the Java virtual machine, involving specific memory allocations and strictly orchestrated CPU cycles. To sustain near-instantaneous retrieval times under heavy loads, Java's HashMap relies on a highly specialized architecture of bitwise logic, strict memory boundaries, and internal structures that physically mutate as data density increases. We are diving past the high-level API methods, straight down into this rigid architecture. Specifically, we will examine exactly how the hotspot JVM translates theoretical O1 algorithms into high-speed, attack-resistant engines. Because if you want to scale a back-end application effectively, you must abandon big O notation as your only metric for collection performance and understand what the hardware is actually doing. The first physical constraint a HashMap faces is mapping an arbitrary 32-bit integer, the object's hashcode, into a usable index for a finite array of buckets. Using a mathematical modulo operation to find the remainder is computationally expensive for the CPU. To solve this, Java forces the map's capacity to always remain a power of 2. This precise boundary allows the JVM to replace the heavy modulo arithmetic with a much faster bitwise AND operation. This diagram demonstrates that bitwise operation in action. By evaluating the hash against the array capacity -1, the AND logic calculates the exact bucket index in a fraction of the time. But there is a severe flaw in this operation. If the table capacity is small, the AND calculation only reads the lowest bits of the hashcode. It completely ignores the higher-order bits, which causes multiple keys to crash into the exact same buckets, creating dense clusters. Here is how the internal spread function mitigates that clustering. Before calculating the index, the map takes the original 32-bit hashcode, shifts a copy of its top 16 bits to the right, and merges them back into the bottom bits using an XOR operation. By folding those higher-order bits downward, the algorithm forces the data's entropy to spread evenly across the entire integer. This bitwise preprocessing guarantees that the map's O1 retrieval speed is protected, even if the developer writes a suboptimal hashcode method that produces poorly distributed values. Moving data quickly is only half the equation. The physical allocation of heap memory enforces a strict byte cost for every abstraction. Internally, a hash map is an array of individual nodes. On a 64-bit JVM, each of these nodes carries a heavy structural payload. This chart breaks down an uncompressed node, a 16-byte header, a 4-byte hash, and 3 8-byte references for key, value, and next. That's 64 bytes of overhead. Passing the use CompressedOops flag cuts those references in half, shrinking the node's footprint to roughly 32 bytes. This precise memory footprint dictates the physical cost of other collections as well, particularly the HashSet. A HashSet does not have its own distinct data structure. It relies entirely on wrapping a private hashmap. Because a map requires a key-value pair, the set must store a dummy object called present for every single entry, purely to utilize the map's uniqueness guarantees. High-speed algorithmic abstractions are maintained strictly through heavy heap memory allocation and pointer bloat. When different keys inevitably map to the same bucket index, Java resolves the collision through separate chaining. Historically, this meant appending each new entry to a linked list inside that bucket. If too many keys hash to the same spot, that list grows. Instead of jumping directly to a value, the CPU must read through every single node one by one, degrading lookup performance from O1 to a disastrous ON worst case. This predictable degradation creates a security vulnerability. Attackers can intentionally feed an application malicious keys designed to hit the same bucket index. This forces the CPU into exhausting sequential reads, stalling the system in a hash denial of service attack. To neutralize this threat, Java 8 introduced a dynamic treeification mechanism. When a single bucket accumulates 8 items, it triggers the treeify threshold. This animation shows the structural mutation. The vulnerable linked list breaks apart and reorganizes itself into a balanced red-black tree. By forcing data into a balanced hierarchy, search time drops from O of n to a secure O of log n. Because tree nodes consume more memory, the map tracks density. If a bucket drops below 6, it triggers the untreeify threshold, shedding overhead and collapsing back to a chain. The HashMap architecture uses these structural transitions to maintain performance, allocating heavier tree nodes only when data density threatens the stability of the collection. Even with treeification, buckets cannot grow indefinitely. When the map reaches 75% capacity, its default load factor, it must double the size of its internal array to maintain overall efficiency. This triggers rehashing, an immense O of n computational penalty, where an entirely new array is allocated and every single existing node must be reindexed. Historically, this required recalculating modulo math for everything, but Java 8 introduced a bitwise split optimization to radically accelerate this heavy operation. Because the new array doubles, a node's position depends on just one bit. If 0, the node drops straight into the same index. If 1, it shifts horizontally by a distance exactly equal to the old array's capacity. By checking a single binary bit to determine placement, the JVM completely bypasses the need to recalculate the full hash for any element. That strict power of 2 capacity rule we looked at earlier exists specifically to enable this split logic, making dynamic array scaling computationally viable at massive data volumes. This resizing operation introduces catastrophic risks in multi-threaded environments. If 2 threads trigger a resize on a standard hash map simultaneously, internal pointers will corrupt, breaking the map completely. To support safe parallel processing, the ConcurrentHashMap evolved from Java 7's architecture of independent segmented locks to Java 8's lock-free compare and swap operations at the individual bucket level. The ultimate bottleneck in scalability is performing a massive O of n rehash without locking out the dozens of active application threads trying to write data. ConcurrentHashMap solves this through a cooperative transfer mechanism, turning thread collisions into processing power. Worker threads attempt to write to a migrating bucket, hitting a marker called a forwarding node. Instead of waiting for the resize to finish, the threads immediately redirect to grab unprocessed chunks of buckets and migrate the data themselves. High-performance JVM scaling depends on this granular thread cooperation to manage memory reorganization without the bottleneck of global synchronization locks. Stepping back from the JVM, the architecture of Java's hash table enforces a strict compromise at the hardware level regarding CPU cache locality. Java's reliance on separate chaining for collision management means each node is an independent object floating on the heap. Following those pointer chains forces the CPU to fetch data scattered randomly across main memory, causing frequent L1 and L2 cache misses. These erratic jumps stall the hardware. The CPU sits idle while waiting for requested memory addresses to arrive from RAM. Alternative designs like open addressing store everything in flat contiguous memory arrays to keep the CPU cache fully loaded, but they collapse entirely under high load factors. Java accepts the cache misses of node-based chaining because its fallback to red-black trees provides highly resilient, predictable stability when the system is under severe pressure. Professional engineering requires looking past the API definitions. True performance is built by mastering precise memory layouts, leveraging bitwise logic, and understanding exactly how code interacts with the physical constraints of the machine.